Hello everyone, I am Manav and my teammates are Lavanya and Isha, and our topic is fraud detection in financial transactions. Let's start with the motivation. While with billions of digital transactions occurring daily, financial fraud poses a growing threat to banking systems worldwide. The impact is massive, from financial losses to damaged customer trust, making advanced fraud detection systems critical to maintaining security and stability. Moving on to the problem statement. We have three major problems which have to be addressed. Traditional rule based systems are no longer effective. They struggle with evolving fraud tactics, generate excessive false positives, and fail to detect complex multi step fraud operations. These challenges demand adaptive, machine learning based approaches that can improve detection while minimizing false alarms. Moving on to the dataset. We have used PaySim, a synthetic yet realistic dataset simulating mobile money transactions over a period of 30 days. It includes 6.3 million labeled transactions with a natural class imbalance, closely mirroring real world fraud detection challenges. The inputs to this data set are the transaction details and the account details. Transaction details include the amount, the transaction type, and the timestamp, whereas the account details include the sender's details, receiver's details, and the balances before and after the transaction. Our output is a binary classification where 0 accounts for a legitimate and 1 accounts for a fraudulent transaction. Now I would like my teammate Lavanya to take over.
For the methodology, we first conducted data pre-processing in which we filtered out transactions for transfer and cash out categories, which basically contained the fraud transactions in our data set. We then performed feature engineering in which we normalized our data and we also converted the categorical values into numerical format using label encoder. Then we conducted class imbalance handling. So we basically undersampled the majority class, which was the class with non-fraud transactions in our data set, and we then applied SMOTE to get a 50-50% ratio for both the classes. We then did the model development in which we started with 128 neurons in the first layer and gradually decreased the width of the layers to 1 neuron in the final output layer. We also used ReLU activation function and 40% dropout. Dropout was used as a regularization mechanism to ensure that the model does not overfit. Now, moving on to the metrics. So, recall is a critical metric for fraud detection system as it measures the model's ability to catch all actual fraud cases, making it more important than overall accuracy or precision. In financial fraud detection, missing a fraudulent transaction, that is, having a false negative, has far more severe consequences than flagging a legitimate transaction for review. While investigating a legitimate transaction might cause temporary inconvenience, missing fraud can result in substantial financial losses. We have also calculated precision and F1 score. An F1 score is calculated to maintain a balance between precision and recall. Now, my teammate Risha will talk about the model architecture.
Our model employs a feed-forward neural network, specifically a multi-layered perceptron, which is optimized for financial transaction analysis. The network processes 10 key transaction features through a funnel-shaped architecture, that is, going from 128 to 1 neuron, progressively refining transaction patterns into fraud indicators. The final sigmoid layer outputs a fraud probability score between 0 and 1. This architecture was selected over more complex models like CNNs or LSTMs because individual transaction fraud depends more on feature relationships than sequential patterns. Now, talking about our optimization steps, the model's training process incorporates several optimization techniques: an Adam optimizer with 0.001 learning rate, L2 regularization, and 40% dropout between layers to prevent overfitting. Training utilizes a batch size of 256 transactions and employs a hybrid sampling approach, that is, 40% undersampling and 50% smooth, to address class imbalance. The classification threshold is dynamically adjusted to maintain recall above 85% while maximizing precision. This is so in comparison with our baseline model, which was XGBoost, which received a resulted in precision being 93.9%, recall being 36.86%, and FN score 0.5294. Our model, uh, while we traded off with our model on precision being 69.9, we focused more on recall and increased it to 85.27%, achieving an improved F1 score of 0.7664. This is our performance visualizations where you can see the confusion matrix and a metrics versus threshold graph, where while our default threshold is zero point 0.5, we went with a threshold of zero point 0.9 for better balance. None of the team members have done any prior work in this project, and we have all started from scratch. This is our reference for our PASM data set, and thank you.